All right. So this is my submission for uh, assignment 2 of machine learning. Um, I have here my all my different codes that I've written. This is for the assignment. This guy. So I need to write a logistic regression algorithm with a 70-30 split for the classification of this breast cancer data set. This was not 100% clear whether it was supposed to be implemented from scratch or whether I could use like PyTorch and stuff. So I just did it both ways because why not? Just do it both ways. That's probably the safest method. And then we're writing a feed-forward neural network from scratch to classify the same thing. So I'll just give you the quick disclaimer at the beginning. This worked more or less with a little bit of nudging. This did not converge. It overfitted every time and would not work. Basically, it would go to, or it underfitted technically, because it would go to 66% accuracy roughly, which is because 2/3 of the data set is non-breast cancer, and then it would just sit there. And even when I balanced the data set, it would still just assign everything to 0 or what have you. So fun. This guy, no work. This guy, no do the thing. But these guys worked okay, especially the one that I did from scratch. That worked really well. So let's open up Spider. We have. Let's start with this guy. So this is my implementation of logistic regression using PyTorch. It's pretty straightforward. You just seed it. I've seeded it so that it's consistent, because I know that seed 1 tends to give me the results that I'm trying to show. We actually fetch the data, put it into the proper data types and all that stuff. Train test split using train test split from sklearn, just because that's not really worth my time to program, and we all know how to do that. The actual logistic regression module, this is just a normal like single layer neural network with a sigmoid output. And the reason why I did that is because our loss criterion is BCE, which should take care of that, all the logistic regression stuff automatically. But that only works with our single output, like our single output node, which is, there's some debate about whether you should do this with a one-hot vector or like one-hot vector with 1 being no cancer and 0 being cancer. But for this implementation, it just was really, really nice to use BCE loss. So I said, it's 1 or 0, and it's going to differentiate between the two, and BCE loss will do the logistic regression for that, which is a little bit different from what we talked about in class, but it's pretty close. And I still have this implementation too, if you're not convinced that I can do that. So learning rate is, as you said, 0.05. We're just basically doing forward pass, calculating the loss, doing backward pass. It's pretty straightforward. We're printing the loss each time, and then we print the accuracy at the end, just to this console. So we can run it, and as you see, it does not learn anything, and that is because the learning rate is too high. If we decrease the learning rate, it will learn. That's why I set the seed, because it actually is a little inconsistent still. With this seed, it always works. If you switch the seeds around, it'll work about maybe 2/3 of the time. It's kind of hard for it to converge because I guess it's such a simple model, or maybe there's just such a small amount of training data, to be honest with you. But the only way this worked is with Atom Optimizer, as far as I could tell. I tried using like SGD and that kind of stuff, and it didn't do the thing. But Atom worked great, so. It does learn, just not with the learning rate that was specified in the assignment, so we leave it this way for our final submission because that's what you requested. Now, this is my implementation of that from scratch because the assignment didn't strictly say whether it was supposed to be from scratch or not, so I did this from scratch just using NumPy. We load in our data, split it, adding, bias and all that stuff. Initialize the weights. Then we have our logistic function, our cost function. So this is basically sigmoid. This is our cost, which is the actual like log rules and stuff. Then we got this guy. I had a little J history here because I was plotting it earlier. I actually don't need that anymore. I can get rid of that. Let me, yeah, I don't need that anymore. So what we have here is pretty simply, we're just taking our weights and we're subtracting from them by the learning rate times the cost function, which is just this logistic function, divided by the amount of instances that we're training. So it's pretty straightforward. This is batch gradient descent. And we're just going to print it to the console just as requested. Yeah, so 91% with this current set seed. If you decrease the learning rate, it does, I think, learn a little more consistently if you change around the random state. But for this one, it always gets 91%, and that's pretty good. It usually, if you change around the random seed, it'll go between like 85 and 95%. So that's pretty good accuracy out of that. Now this is our neural network, and this was the wild child of this assignment. Let me do our set seed, because why not? It doesn't make a difference. This thing never learns. It gets 63, sometimes 65% accuracy each time. This overflow error is just because of this softmax, or no, it's the sigmoid implementation. Because I guess the weights go to 0 or something, and that screws up the exponential calculation, which makes sense. It's just dumb. I have not been able to get this to work. It does not work with any learning rate that I've been able to try. It trains, it attempts to train, and it goes through all the data, but it does not converge. And you gave me the exact network dimensions and learning rate. So if you can find anything wrong with this implementation, feel free to point it out. But I'm pretty confident that the architecture that we were given is just inherently not able to actually learn anything useful from this data set. So I'll run it. It always gives you, even if actually I can just disable the random seed for now. Just disable the set seed. So yeah, it always gives you about 66%, because that's the train, or that's the split between breast cancer and non-breast cancer patients in this data set. So yeah, this is like all this is doing is forward pass, softmax. It's got bias and all that stuff. We're zero initializing our bias, which is pretty normal. And backwards pass, it's just computes the output error. That's just L1 error. And then boom, get the hidden error. This is not complicated. All we're doing is just subtracting the learning rate times our error calculations, essentially, or the dot product of our error calculations with the inputs, which is the way that this is supposed to work. Yeah, with the neural network implementation and architecture that we were told to make, I don't think that this can converge. Somebody might prove me wrong in this class. It's entirely possible, but I have not been able to get it to converge, even playing around with this learning rate and all that stuff. I suppose I could try doing the thing that I did here and implement my own Atom optimizer, but I don't want to do that because that sucks. Also, technically, this is not a fixed learning rate anymore because we're using Atom, so it's also not quite what was intended for the assignment to begin with. So yeah, This one's a bit of a weird one. I don't think this can actually work, but the logistic regression works great. This neural network architecture is just a little bit, it's not quite right. And there's nothing as far as my programming goes, I don't think there's anything I can actually do about that. It's just the network architecture that we're given is fundamentally not able to learn this for one reason or another. I mean, maybe there's some random initialization where it can, but I have not been able to find it. So yeah, that's my submission. All this code is going to come to you. Have a great day.